So today we're going to look at the design model for Uber and YouTube. But before we do that, I know yesterday we had started looking at the case study and system design model for WhatsApp, and I think it will be really nice if we go back there and check through a few things that we had missed out on. So let me go back to WhatsApp because we had not actually finished reviewing it, and I believe it wouldn't be nice if we leave it pending. So just an overview on what we covered yesterday. Yesterday we looked at what system design actually is, from both an overview layout to much more complex aspect, and we decided to come up with three major system design aspects that are very clear, are very key, and we had started looking at WhatsApp system design, and we realized that yes, they have a very high level architecture, which is clear, and this high level architecture is based on a few things from various kinds of authentication services, how queues are passed through, notifications, and other more things. And then we also looked at message sending flow, how messages are sent from the sender to the receiver. We realized that there's an API gateway, and also there's how this messaging service operates, how it's validated and routed to the messaging service aspect, how it's published, and other more areas in terms of queues and also message storage. And then also there was message delivery with offline support, which we also looked at, and also media upload and delivery flow. We looked at this flow clearly. So today, we had also tried to look at present system, how you can be able to, check whether, the last scene of, someone on the other end, whether it's clear or not. That was also very interesting to discuss. So we were supposed to get to now end-to-end encryption flow, and this is where I want us to look at today as we continue. So one thing that you'll be able to understand is that WhatsApp has a very high security, and actually even today, you realize that there's some features that have been added to WhatsApp, and one of them is the advanced security feature. I've also seen a new feature rolled out where you can be able to translate messages to different types of languages, maybe from English to Swahili, or English to different types of languages. But what I'm not sure about is like it's been trained on the traditional languages, which I believe they should be working on that. Okay, so when it comes to end-to-end encryption flow, the key thing here is in regards to security. How is the message being sent by the sender encrypted, and how is it encrypted in the server, right? And how does the receiver get to receive this kind of a message? So there are different things here that are very, very important. First of all, the sender getting to send the message, we expect that that message already is encrypted, right? Because on your end, before you think of sending the message or even typing the message, it's already encrypted on your end. So once you get to send it to the receiver, it passes through a few it passes through some levels. One is it passes through the server, which means that the message is sent to the server as an encrypted message. So you can't be able to bypass the message before it's sent to the receiver. So it has to be encrypted. Once it gets to the server, there's some engineering operations that takes place to the server to a point where now it's sent to the receiver, where we now call that forward ciphertext. So this is just an overview view of it. I'm just trying to give you an overview engineering layout of how an overview design engineering layout of how an end-to-end encryption flow looks like. And as you can see here, we're talking about message encryption, which is actually already encrypted from the sender, and then the message now is sent through the server, as you can see here, and thereafter it's forwarded as a ciphertext to the receiver. So once it's sent to the receiver, the message now gets to be decrypted. So it's the receiver who gets to decrypt the message and then gets to read it. So there are different processes that, as you can see, are very clear uh, in ways that explains how encryption flows, or rather how encryption actually works from end to end. So apart from that, you realize that the server needs to read the message content. So that's what I'm talking about here. The server here gets to read the message content. I mean, okay, sorry, it doesn't read the message content. I'm so sorry about that. This server never reads the message content. Keys exist only on user devices. These keys exist only on the user devices. So the users here are the sender and the receiver. So the sender gets to send the message, the receiver gets to read the message. So the receiver gets to decrypt the message that has been sent by the sender, which is encrypted. Well, when you say encrypted, it means that this message is only known by the sender, right? And it's encrypted. So when the sender gets to send it to the receiver, it has to pass through the server. Once it passes through the server, it's forwarded as a ciphertext, and then the receiver gets to decrypt the message and reads it. So that's how the whole um, sending and receiving of text messages from WhatsApp um, takes place. It's just that's how the flow looks like here. Um, there's also what we call group messaging architecture. Group messaging architecture. We're talking about how can you be able to send a message to a group and be able to read all the group chats of all the people who are actually chatting or rather sending text messages there. So first of all, you realize that you as the user, you're part of that group. So as a as one of the people in that group, there's some processes or rather there's some procedures that your text message takes to be able to be received by all the other users out there. So when you're in a group chat, or rather when you're in a WhatsApp group and you want to send some text message, there's some architecture that your message goes through to a point where now all the other users get to receive your message. So you as the user, you get to send a message and then it goes through what you call a group service. So once it goes through a group service, it's split through one, group metadata, and then two, message funneled. So once it gets the message funneled, it's now dispersed to various users. Now here you can see we have user one, we have user two, and then we have user three. So the process here, how the process looks like is you're able to ensure that your message reaches all the other people down here. And this is just three, but then you can always imagine the number of people in various WhatsApp groups. If a WhatsApp group can house around maybe 1,200 people, and when you get to send a message, everyone will be able to see your message. You can try to imagine how the architecture in a group messaging looks like. So that is one thing that I'm really trying to, talk about. So it's just an overview bit of it. I was just trying to get you to see the system design aspect on how this actually looks like. And then we have what you call scalability architecture. We have what we call scalability architecture. So when it comes to scalability architecture, one is what we call load balancer, and this load balancer is split into three servers. One we have, server A, server B, server C, right? And then now there's Redis. Now from Redis to the database. So the database is where all the data is stored, right? So this load balancer supports these three app servers here, right? And then all of them are sent to the Redis, and then from the Redis to the database. So and yesterday I introduced Redis, and you also how Redis has been very effective in ensuring that you can be able to connect more with the database and even send messages. I mean, not send messages, but rather retrieve messages clearly. Um, there's also what you call failure handling design. Someone has a question? Someone has a question? There's also what we call failure handling design. What I mean by this is, yesterday we realized that one of the key reasons why system design is important is to ensure that when there's a breakdown, or rather when a system is down in a way, it's easier for for it to still kick back to life and continue regardless of the failures that it has. And those backups are very important because they help to ensure there is that um, balance in how everything is operating. So there are various ways in which you get to handle failure, and one of them is, especially how WhatsApp gets to do it is different. So here we have a client, and this client is connected to an API. Then a failure occurs here. Then there's what we call a retry queue, then a fallback service, then user notification, right? So how failure is handled here is very beautiful because you realize that in as much as the client will be able to connect with the API, that retry queue here will ensure that you can be able to fall back, the service can be able to fall back, and then the user gets to be notified on what has actually went to has actually gone around. So it's just as simple as that when it comes to handling failure. And there's what you call what subsystem design summary, just to give you an overview on the components and the purpose of all this. The main purpose of an API gateway is it acts as an entry point. So mostly when you have a system architecture and you want to connect various kinds of APIs gateway, you're trying to give way for specific kinds of data through a specific point. So that's why we call them entry points. They're more, um, they help you to access various kinds of gateways. We call them API gateways. Very interesting. Then we have what we call messaging service. So messaging service, the purpose of a messaging service is to help you in message routing, right? To help you in message routing. Then we have what we call queue. So the purpose of queue is to act as an async processing, also very, very important. Then we have Redis. So Redis, the main purpose of a Redis is it acts as a presence plus keychain. So presence plus keychain, very important. Then we have object storage, helps to store things to do like media and other things. Then we have CDN. This is content delivery network. It's very important. It helps in the fast delivery of content from one end to another. Then encryption basically is privacy. Then load balancer is for scaling. So this is just the WhatsApp system design summary to give you an overview of how all these components operate and even their purpose. From the API gateway, it's an entry point. The messaging service is message routing. The queue is the async processing. Redis is for presence plus caching. Object storage is for media. CDN is for fast delivery. Encryption is for privacy, and then load balancer is for scaling. So there's some key design principles also that I would like us to look at. One of them is event-driven architecture. 2 is asynchronous processing. 3 is horizontal scalability. And 4 is fault tolerance. Then 5 is low latency delivery. Then we have strong encryption. Then geo-distributed systems. So these key design principles are very important because they help you to understand various kinds of not just architecture, but even processing required in ensuring that the system is perfect and doesn't lag at the end of the day. There's some interview ready talking talk points. I mean, there's some interview um, areas that are also very important because they are mostly tested. One is why WhatsApp uses message queues. So most of the time, these are some of the questions that you might be asked in regards to WhatsApp. Why WhatsApp uses message queues, how Fanout works for groups, why Redis is critical, why CDN is needed, how WhatsApp achieves low latency, how end-to-end encryption works, how to handle millions of concurrent users. So these questions are very important, and I'll be so happy if you try and work them out on your own. So you can take this as a takeaway assignment. Try and go and answer these kinds of questions just to make sure that you can be able to at least understand most of these key areas, right? Are we good, Faith? Hello?
Yeah, we are good.
Okay.
Hello.
Okay, good.
Uh,
Yeah,
I have a question
yes, Faith.
about I wanted to ask how WhatsApp handles that typing indicator for the million or the billion users.
Oh, yeah. So that is here. It's one of the assignments you're supposed to take, how it handles millions of concurrent users. So I want you to go and look into that, and then we can have this conversation tomorrow. Is that okay?
Yeah, fine.
Yeah. All of you go and look through this, and then we'll have this conversation once we meet tomorrow. Then there's what we call final note. So this architecture supports billions of messages a day. I mean, you can imagine the number of messages WhatsApp accesses every single day. They're in billions of numbers, and then also there's millions of concurrent users. So we're talking about messages. We're talking about users. Users here in millions of numbers. Then there's what we call a near zero latency delivery. Then there's what we call high fault tolerance. And then there's secure communication. So this architecture, as you can see, it might look simple, but the kind of task that it solves is a big one. It gets to handle billions of messages a day, millions of concurrent users, near zero latency delivery, high fault tolerance, and also secure communication. So it's very, very important. Very, very important. So that was that is all about WhatsApp, and I'm glad that we've been able to look into that. I would like us to now get to Uber and YouTube. So this is also case studies, and I want us to now do a comparison between WhatsApp, Uber, and YouTube. And this is basically a production grid analysis just to help you see how clearly this operation is important. Um, let's go through the table of contents first of all. So from the overview bit of it, we have Uber system design. So here we have requirements, we have architecture, we have core components, we have data flow, we have matching algorithm, we have scaling challenges, we have failure handling. Then now we go to YouTube system design where we have requirements, architecture, video upload flow, video streaming flow, recommendation system, storage strategy, scaling and optimization. Then we have advanced design consideration and then summary comparison. Then let's look at now the overview bit of it here. So these case studies focus on one, real world scalability, two, high availability, three, low latency, four, fault tolerance, and five, we are talking about distributed system design. So they are structured to match FANG interview expectations and production architecture standards. And that is actually the reason why we have to look into them, because they help you to understand what are these production architectural standards to look at, and how can we ensure that our system design is strong and very foundational. So let's look at the Uber system design. So we have what we call functional requirements. So one, the user requests the ride, then the driver accepts the ride. As you can see, most of the time when you use Uber, you as the user, you get to request a ride, then the driver accepts the ride. So the driver gets to accept the ride simply because they are within the vicinity around you, and they would like to come and drive you around. Then real-time location tracking. So that is very important because the driver and the user, they need to know where the car actually is, or rather where the driver actually is. Same case for the driver. The driver needs to know where the user actually is, or rather where the client actually is. So without that real-time location tracking, it's very hard for that to happen. And then we're talking about fare calculation. Fare calculation means how much will it take to move from point A to B, right, from here to there. And then payments. So payments also very important. And then the ratings for the driver is important. This is actually very good for the user. So these are just some of the functional requirements for our Uber system design. Then we're looking at now non-functional requirements, which are also very important. So for the non-functional requirements, one of them is low latency. So this could be less than 200 ms, and then we have high availability. Then we have real-time updates, and then horizontal scalability and fault tolerance. So when it comes to non-functional requirements, it's also very important for us to note how effective it is, because this low latency update is very important. High availability of the driver, real-time updates, horizontal scalability, fault tolerance are very important. So let's now try and look at the high-level architecture. Let's look at the high-level architecture here. So remember, this is Uber, and the architecture is very interesting to look at, because we're dealing with both the user and the driver. So I want us to understand how the user app looks like and how the driver app communicate together to ensure that the services being offered are effective. So the user app, rather the driver app too, they all get to send request messages. So the user gets sent a request message, and it's sent through the API gateway. Then the driver gets to accept it, right? All of them in the API gateway. Once that is done, there's the authentication service here. So definitely the API gateway is authenticated. So that's why it's easier for the user to not really penetrate through, but the driver can be able to know what exactly is going on the user's end, same case, but the user can't be able to create the driver application unless they are authenticated to do that. So that authentication service is very important here. And then we have what you call ride service. So for the ride service, now the user, or rather the client, gets to send a request whether they need a ride service. So that will depend with how the API gateway will read the message. If it's supposed to be a payment, it will go to the payment service. If it's supposed to be a notification service, it will go to the notification service section. And remember, all of this is taking place. Everything is being redirected from the API gateway, as you can see. So when you go to the ride service, as you can see here, this is what we call the location service. So the location service of the actual user, and same case for the actual driver, it's here. Then the matching engine is here, and then the database. So the database gets to store everything. And then now we have what you call the Redis cache. So I hope up here you had seen what the Redis cache gets to do. So Redis, we said it gets to cache. Oh my God, I've missed it out on the WhatsApp system design aspect, but it's okay. So that is the Redis cache, and it's very important to actually get to know its functionality at a much more deeper level. So we have core components, and I would like us to look into them. The API gateway. So in the API gateway here, there's some things going on. One is authentication. As you can see, there's authentication here. And then there's also what we call rate limiting. It takes place in the API gateway. There's authentication, there's rate limiting, there's routing of the user and also the driver. There's a request validation, right? There's a request validation. So that's what is taking place in the API gateway. Then we have what we call ride service. So ride service, this is where the ride is created, and then the status management takes place. And then there's what you call a trip life cycle. There's the ride creation, there's a status management, then there's a trip life cycle. That's what I'm talking about when you come here, to the ride service. And then we have what you call location service. So for the location service, which is here, it's connected to the GPRS so that it can be able to detect. So it has the real-time GPS updates, not GPRS, GPS updates. And then also we have the geo indexing there. And then there's the driver proximity search. So all of them is in the location service. So remember, every section, you need to ensure that you can be able to explain what is going on there, right? So we also have the matching engine down here. So the matching engine, I hope you can see here, this is the matching engine. We've already talked about location service, ride service. Now we are here on the matching engine. So in the matching engine, we are trying to find the nearest driver. So if you're going maybe from Westlands, from maybe CBD to Westlands, or rather from Westlands to CBD, you have to find the nearest driver around you. So this matching engine will consider a few things like distance, availability, the driver rating, and ETA. ETA basically means estimated time of arrival. So the matching engine here is very effective in ensuring that you can be able to find the nearest driver around you, and to consider the distance between you and the driver, the actual availability of the driver, the actual driver rating, and the ETA. Again, we have what we call matching flow. So when we're talking about matching flow, now here we're trying to understand how does the whole flow from the user to the driver application works, right? And what is the engineering around, what is the system design around it? That is what I want us to look at from this layout that we already have. So as a user, you get to request a ride, and when you request a ride, it goes through the API. So from the API, you get to create a ride, and then it goes to the ride service. Then from the ride service, you get to fetch nearby drivers. So when you get to fetch nearby drivers, you get to do that based on the location of the drivers. Um, Depending with the other drivers are they nearby you, are they far away from you? So basically, you always want the nearest driver who can take you from point A to B very easily. And then after that, we have a driver list. So a driver list goes to the matching engine, and then now there's a ride request that is taken, that is signified to the driver application there. So the driver gets to now accept, because up to this point we expect that the driver has been able to has been able to see a request from the user. So they get to accept it, and then it's sent to the matching engine. Thereafter, the ride is confirmed and sent to the ride service. Thereafter, it's sent to the user. So that process is very important in ensuring that there's that effective communication between the user and the driver, right? So there's a user app here, and then there's a driver app here. So the user gets to request a ride. This is sent through the API. Then the API indicates that there's a ride that has been created, and then after that, the ride service gets to fetch the nearby driver, and based on the location service, a list is provided, and this list is matched through the engine, and then the nearest driver is sent a request, right? After that, the driver gets to accept the request, then the ride is confirmed, and then the ride is sent to the user. And that is how the flow actually works. As clear as that might look like, it's very fast. You see, when you're on standby and you want to quickly get an Uber, you realize it won't even take 2 or 3 minutes. Okay, maybe 2 minutes to make sure that the driver has actually confirmed that they are coming, but mostly it's very, very fast. This process is very fast. You can't even imagine that this is the system design required in ensuring that this process is smooth like that. So these are some of the things that we tend to ignore because we don't always try to understand the engineering aspect of this solution. Now this is the point where you get to appreciate the designers and engineers of these kinds of products. So I want us to look at something called data storage strategy. How do we get to store our data? So the user profiles mostly are stored in our SQL. So here we are talking about things to do with databases. The user profiles are stored in the SQL. The trip histories are stored in the SQL. The driver locations are stored in the Redis, and then analytics are stored in the data warehouse. So this data storage strategy is very important, and as you can see, it's super important. Then we have scaling strategy. So scaling strategy. Yesterday we had looked at scaling strategy on WhatsApp. We saw there's horizontal scaling and then there's vertical scaling, and here we're looking at now various scaling strategies used in Uber. So let's start by the horizontal scaling part. So when it comes to horizontal scaling, there's what you call stateless services, and then there's what you call load balancers, then there's what you call auto-scaling groups. Then for caching, we have Redis for active rides, then we have Redis for driver locations, right? And then we do have what we call geoshading. So for geoshading, we're looking at partition data by city or region. So here you get partition data by city or region. So if you're in Nairobi, Kenya, you get partition data by Nairobi, right? Maybe if in Kisumu, you get partition data by that region. So partitioning data by city or region is very important. That's what we call geoshading, right? And thereafter, there's something called failure handling. How do you get to handle failure just in case? For example, if your driver drops, so the solution majorly is to reassign a driver very, very fast. Then if the service crashes, you have to retry plus do a fallback. So that's the solution towards that. And then if there's a payment failure, you get to retry, then check the wallet again. Then if there's a location failure, you have to cache your GPS. So these are just ways in which you as the user, now this one is typically the user trying to handle failures at the end of the day. The driver drops, you get to reassign a new driver, which means you get to look for a new driver from the application. If the service crashes, you get to retry back, and also it gives you a fallback. If there's a payment failure, you still have to do a retry and then check the wallet. If the location fails, you have to cache your GPS. So those are failure handling methods that are very important, but I bet these are clear to everyone. And then there's what we call bottlenecks and solutions. So, for example, when we're talking about high latency as a problem, the solution here is coming up with a geo-replication. Geo-replication basically is a geographical replication so that it's easier to, and then when talking about hot partitions, we get to do shading, right? When talking about driver overload, we get to do throttling. When we get to do a surge demand, the solution here is to do what we call dynamic pricing. So these bottlenecks and solutions are very, very important. And then we have what we call YouTube system design. So up to this juncture, we've looked at Uber system design, and I would like to get a few questions before we get to YouTube system design. Any questions before we get to YouTube system design? Someone has a question? So something about YouTube system design is that there are functional requirements and non-functional requirements, just like we had looked at Uber, right? Are we here? Hello.
Hello.
Okay. Are we together?
Yeah, we're together.
Okay. Yes, David.
Can you, okay, can you tell us about the project that the people who you teach in the morning are doing? Like a
Yeah.
brief of
So
it.
one thing that we are really heavy on is product development. So product development basically means getting to build solutions that are market ready. Market ready to mean that these are solutions that the market can be able to acquire, and so everyone in that group is actually building a specific product in a specific area. It could be in fintech, in agriculture, in clean technology, or even in health technology. So what they're supposed to do, rather what you're supposed to do, you're supposed to go out, look for a problem statement, and make sure that that problem that you're trying to tackle is very simple but very scalable. Yeah. And it's a pain point problem in the market. So at the end of the day, you need to figure out how you can be able to implement it using the already existing technologies. So you can get to do that as an individual, or you can get to do that as a team. And that is very, very important because you get to learn from a practical perspective. So you find even when we are going on with these sessions, you are also building something on the side. And that is one thing we are really heavy on. So you guys are supposed to start doing this next week, not this week. But I wanted just to make sure that the orientation and this whole process is effective, because I believe that the instructor earlier on wasn't really um, uh, ready and clear on everything you guys are required to be doing. So at the end of this course, you're supposed to graduate with a product that's already in the market, right? And then that's when you can get certified. That's the most important thing, and we're really heavy on that. We're trying to be pragmatic, right? So on your free time, try to think through a problem, right? And make sure that problem is a problem that is clear and is it's solving a very important issue in the community. Um, yeah. So that's what is going on with the other team, and I'll be glad if you guys also start doing that from next week. And as we continue our sessions in the evening, you get to also build on your free time, because everything, now that you have our GitHub Research Hub, you'll be able to now build your own. So you'll be doing this individually. Everyone will be building their own product, and you'll be pushing the changes on our GitHub Research Hub. Is that okay? And they will be private, actually.
Yeah, it's fine.
Yeah. So all this is supposed to take place from next week, but between now and Sunday, let us focus more on our usual learning. We don't always have classes on Saturdays and Sundays. Mostly it's from Monday to Friday. Saturdays and Sundays majorly are for external sessions. Sometimes we invite guest speakers from various tech companies to come and share with us what it looks like from their end. But the most important thing is to ensure that you are building something as an individual, and that is one thing we're really emphasizing on. Technology is all about being pragmatic and also being very practical with your skills. So that being said and done, I think um, you all now at least have an idea of what is expected of you. Is that okay?
Yeah.
Okay, good. Any other question? Any other question? Someone? Anyone? Okay, I bet the silence means we are good. I wish you all a very beautiful night ahead of you, and see you tomorrow. All the best.